Welcome to this lecture on Solutions to Exercise 5.4, Question 9 to Question 16 from the book Introduction to Real Analysis by Bartle and Sherbert.
Welcome everyone to the second part of the solution to exercise for section 5.4 from the book Introduction to Real Analysis by Bartle and Sherbert. So in this part we will solve from question number 9 to question number 16. So let us start with the question number 9. So in question number 9 we are given a uniformly continuous f and we have to show that its 1 by f is also a uniformly continuous function provided the function has a lower bound which is positive on the domain of f. So let us start with its proof. So given f is uniformly continuous on A and fx is greater than equal to k, which is greater than 0 for every x in A, to show 1 by f is uniformly continuous on A. So to show that 1 by f is uniformly continuous on A, we will take any arbitrary epsilon. So let epsilon greater than 0 be any real number. So we start with any epsilon greater than 0, then consider for any xy belonging to S, because we have to find some delta, so we start with any epsilon. So we start with 1 by fx. So we start with 1 by fx minus 1 by fy. So this is equal to 1 by fx minus 1 by fy. So this is nothing but your, so when you will take the LCM, this is your fx minus fy upon modulus fx modulus fy. Now when we will replace because this fx and is greater than equal to k for every x in k, so we will replace this fx and fy by k, so our denominator will reduce, so overall the number will increase. So we have this greater than equal to sign. So since fx is greater than equal to k and fy is also greater than equal to k, so what delta we should choose? We should choose delta equal to, let delta equal to epsilon times k square greater than 0. Then clearly by the choice of delta, it is evident that one by fx minus 1 by fy is less than epsilon whenever our x minus y is less than delta. So by definition of uniform continuity, 1 by f is uniformly continuous on A. So this completes our proof of question number 9. Now let us move to question number 10. So in question number 10, we are given a uniformly continuous function. So we are given a uniformly continuous function on a bounded subset A of R. We have to show that f is bounded on A. So let us start with its proof. So given f is uniformly continuous on A first, and second, A is bounded. So we are given two things and we have to show f is bounded on A. So for this, what we will do, we will generate a sequence. So we will take the counterpositive approach. So suppose on the contrary, f is unbounded on A. So then then for each n belonging to n, because your function is, this f is unbounded on a, so there exists xn belonging to a such that f of xn is greater than n. So f of xn is greater than equal to n. For each n there exists xn belonging to a such that f of xn is greater than equal to n. So mark it as star. So now, so because f of xn is this f of xn is greater than equal to n. Now xn is a sequence in a and a is bounded, so this implies xn is a bounded sequence in a. So by Bolzano-Weierstrass theorem, xn has a convergent subsequence. So there exists a convergent subsequence xnk of xn. Now, so this xnk being a convergent subsequence is a Cauchy sequence. So then xnk is a Cauchy sequence in A being a convergent sequence. So xnk is a Cauchy sequence, and since f is uniformly continuous on A, so f of xnk is a Cauchy sequence in R. So fxnk is a Cauchy sequence in R, and we know that every Cauchy sequence in R is convergent. In fact, we know that a sequence in R is convergent if and only if it is a Cauchy sequence. So fxnk being a Cauchy sequence is convergence, that is limit. So fxnk is, so we know that every Cauchy sequence in R is convergent, but from star, the star, from the star, but from star, we know that f of x and k is greater than equal to nk, which is greater than k. So f of x and k is a divergent sequence. So from here we know that f of xn is a convergent sequence, and every convergent sequence is bounded, but here we are, and every convergent sequence is bounded, so this is a bounded sequence, but f of x and k is unbounded. So this implies f of x and k is an unbounded sequence and hence not convergent, which is a contradiction. It is a contradiction to say this double star, to this double star. So here we have shown that f of x and k is a convergent sequence, but here we are saying that f of x and k is a not convergent, being an unbounded sequence. Hence, our assumption is wrong, and f is bounded on. So what basically we have done is we have taken the contrapositive approach. So we have assumed that f is unbounded on A, then we are able, for each n we are able to find some point xn such that f of xn is greater than equal to n. So we are able to generate a sequence in A such that its image sequence is unbounded. Now xn is a sequence in A and A is bounded, so by Bolzano-Weierstrass theorem it will have a convergence of sequence, say x and k. Now x and k being a convergent sequence, it is a Cauchy sequence. So x and k is a Cauchy sequence in A. So by because f is uniformly continuous on A, so by a result that we have done in continuous extension theorem, f of x and k is a Cauchy sequence in R, and we know that every Cauchy sequence in R is convergent. So f of x and k is greater than or equal to nk, which is greater than k, and this implies f of x and k is an unbounded sequence, which contradicts the fact that f of x and k is a convergent sequence. So hence our assumption is wrong and f is bounded on A. Now let us take the question number 11. So this is question number 11. So gx is equal to root x is given on the interval 0 to 1. We have to show that there does not exist a constant k such that gx is less than or equal to kx for all x belonging to 0 1. So basically we have to show that for each k there exists some x in the interval 0 to 1 such that gx is greater than k times mod x. And then we have to use this result to show that the function g is not a Lipschitz function, and we will also have to show that it is uniformly continuous on 0 to 1. So let us start. So first claim 1, we have to show that there does not exist any constant k greater than 0, such that mod gx is less than or equal to k times mod x for all x belonging to 0 to 1. So for this, let k greater than 0 be any real number. Then by Archimedean property, or we can directly say there exists n belonging to z positive such that 1 by n is less than 1 by k. Because k is greater than 0, so we will take 1 by k and we will apply Archimedean property. That is, we are taking the integer which is greater than k. So we are taking the integer which is greater than k. So let x equal to 1 by n square. So we are taking x equal to 1 by n square. Now consider mod of gx. So this is mod of gx is equal to mod of root g 1 by n square, which is equal to mod of root 1 by n square, which is equal to, so root 1 by n square is 1 by n. Now this is equal to n dot n square, which is greater than k dot 1 by n square, since n is greater than k, and this is k because, so this is nothing but k times mod x, because x is equal to 1 by n square, so this is k times mod x. So hence g of x is greater than k times mod x. Now since k greater than 0 is arbitrary, hence the claim follows. Since k greater than 0 is arbitrary, so claim 1 follows. So we are able to show that we cannot find any k greater than 0 such that gx is less than or equal to k times mod x for all x belonging to, because we had started with any arbitrary k and we are able to find an x, we are able to find a x such that jx is greater than k times mod x. So first, so this result we have proved that gx is never less than or equal to k times mod x. Now we have to show that g is not a Lipschitz. So first we have to show that g is uniformly continuous on 0 1, and then we will show that g is not a Lipschitz function on 0 1. So for that, let us start. So claim 2, g is uniformly continuous on 0 to 1. So for this, what we will do is, we will, so by uniform continuity theorem, g is uniformly continuous on 0 to 1, because every continuous function on a closed and bounded interval is uniformly continuous. So g being a continuous function is uniformly continuous on 0 1. So we are, so uniform continuity theorem. So by uniform continuity theorem, G is uniformly continuous on 0, 1. Now claim 3, G is not a Lipschitz function on 0, 1. So this we have to deduce from the given result. So we will use this fact. So basically what we have to show, that for each k, so by hypothesis, by part 1, by claim 1, for each k greater than 0, there exists xk belonging to 0, 1 such that g of xk is greater than k times mod xk. Because we are given in claim 1, we have shown that for each k greater than 0, there exists xk belonging to 0, 1 such that g of xk is greater than k times mod xk. Now this implies g of xk minus 0 is greater than k times xk minus 0, that is g of xk minus g of 0 is greater than k times xk minus 0. So we are able to find a pair of points xk and 0 such that this does not satisfy the condition of uniform continuity. So hence, sorry, Lipschitz condition. So hence G is not a Lipschitz function on 0 to 1. So we are able to show that G is not a Lipschitz function on 0 to 1. So this completes our question number 11. Now let us move to question number 12. So in question number 12, we are given a continuous function on the closed interval, on the interval 0 to infinity, and we are given that it is uniformly continuous on the interval a to infinity where a is positive, and we have to show that f is uniformly continuous on 0 to infinity. So we are given, first, f is continuous on 0 to infinity. Second, f is uniformly continuous on a to infinity, and a is greater than 0. And third, so to show f is uniformly continuous on 0 to infinity. So for this, so to show f is uniformly continuous on 0 to infinity, we will start with any arbitrary epsilon. So let epsilon greater than 0 be any real number. Now what we will do is we will show that the function, we will use this continuity fact to show that it is uniformly continuous on 0 to a plus 1. Now by uniform continuity theorem, since f is uniformly continuous, since f is continuous on 0 to infinity, in particular on 0 to a plus 1, so by, okay, let us write on the next page, in particular on 0 to a plus 1, so by uniform continuity theorem, f is uniformly continuous on 0 to a plus 1. So for above epsilon greater than 0, there exists delta 1 greater than 0 such that fx minus fy is less than epsilon whenever x minus y is less than delta 1 and xy belongs to the interval 0 to a plus 1, and xy belongs to the interval 0 to a plus 1. So mark it as star. So we are able to show that fx minus fy is less than epsilon whenever x minus y is less than delta 1 and xy belongs to 0 to a plus 1. So it is important to note that I have taken this interval 0 to a plus 1 because I want the intervals to overlap, because we are given we are given this, we are given the function to be uniformly continuous on this interval, we are given it to be uniformly continuous on this. So to so now we are, what we are going to do is we are going to prove that it is uniformly continuous on something bigger than this, because then they should be overlapping, then only we can club the two intervals and we can say that the function is uniformly continuous over the union. So the function will be uniformly continuous over the union provided they overlap. So that's why we have taken this overlapping interval. So that's why we have taken a plus 1, so that there is overlap here. So this overlap must be there, there should be some overlap. So you could have taken any number greater than a, so we have taken a plus 1 because we can go till infinity, so we can have anything greater than a. So you can take a plus 1, a plus 2, anything greater than a. Now let us come back to this. Now as f is uniformly continuous on a to infinity, so there exists delta 2 greater than 0 such that fx minus fy is less than epsilon whenever our x minus y is less than delta 2 and xy belongs to a to infinity. So this result holds when xy belongs to a to infinity, and this result holds when xy belongs to 0 to a plus 1. Now let us call it as double star. Now let us start with any epsilon. So let delta equal to minimum of delta 1, delta 2, and one more thing. So as I said that we need overlapping, so this distance I need. So whatever point you are taking here on the right of a, you should take the distance between them. So here the distance I have chosen is 1, so I can take minimum of this delta equal to minimum of delta 1, delta 2, and 1. You could have any, if you have taken any point b greater than a, so you could have taken the distance b minus a. So then let delta equal to minimum of delta 1, delta 2, and 1. Then for any xy belonging to 0 to infinity with x minus y less than delta, we have first x minus y is less than delta 1 because our delta is smaller than delta 1. Okay, and second x minus y is less than delta 2 because our again delta is minimum of these two. And third, either xy both belongs to the interval 0 to a plus 1 or xy belongs to the interval a to infinity. So because of this one, because of this overlapping condition, so we are able to get that we will, there will be no situation where x will be here in this and y will be in this. So both have to belong to either this interval or either this interval. So that's why we have chosen this overlapping intervals. So then because of this, because our delta is smaller than 1, so xy can either be in the interval 0 to a plus 1 or both are belong to the interval a to infinity. But it is not that x belongs to this but does not belong to this, and y belongs to this but does not belong to such. That situation will not occur because we have chosen such a delta. So because now x minus y is less than delta 1 and x minus y is less than delta 2, and either xy belongs to this or xy belongs to this. So from either xy will satisfy this condition or xy will satisfy this condition. So if xy satisfies this condition, then we get fx minus fy less than epsilon. If xy satisfies this condition, then we get fx minus fy less than epsilon. So in either case, we are getting that. So from star and double star, it follows that fx minus fy is less than epsilon. So hence fx minus fy is less than epsilon whenever x minus y is less than delta and xy belongs to 0 to infinity. So thus f is uniformly continuous on 0 to infinity. So this completes our question number 11. Now, 12. Now let us move to the question number 13. So in question number 13, we are given a function f which satisfies the property that for each epsilon there exists a function g epsilon such that g epsilon is uniformly continuous on A and fx minus g epsilon is less than epsilon for all x belonging to A, and we have to show that f is uniformly continuous on A. To show f is uniformly continuous on A, so we shall start with any arbitrary epsilon. So let epsilon greater than 0 be any real number. Now we will choose another epsilon naught. Let epsilon naught equal to epsilon by 3 greater than 0. So by hypothesis for epsilon naught greater than 0 there exists a function. So for each epsilon there exists a function. So for epsilon naught greater than 0 there exists a function g epsilon naught from A to R such that g epsilon naught is uniformly continuous on A and fx minus, or you can, and fx minus g epsilon naught x is less than epsilon for all x belonging to A. So mark this as star. Now as g epsilon naught is uniformly continuous on A, so for epsilon naught greater than 0 there exists delta greater than 0 such that g epsilon naught x minus g epsilon naught y is less than epsilon naught whenever x minus y is less than delta and xy belongs to A. So mark this as double star. Now, now for any xy belonging to A with x minus y less than delta, consider fx minus fy. So we can write fx minus fy in terms of g epsilon naught. So we will add and subtract g epsilon naught x and g epsilon naught y minus fy. So what we will do is we will club these two terms, we will club these two terms, and we will club these two terms, and then we will use the triangle inequality to get this. So this is less than equal to fx minus g epsilon naught x plus g epsilon naught x minus g epsilon naught y plus g epsilon naught y minus f of y. So now this is less than epsilon naught by our from star we know that this is less than epsilon naught, also this is less than epsilon naught. So from star we know that this is less than epsilon naught, this is also less than epsilon naught, and this one is also less than epsilon naught because our xy is such that xy x minus y is less than delta. So we can apply double star also and we can apply star also. So which is equal to 3 epsilon naught and which is equal to epsilon. So hence fx minus fy is less than epsilon whenever x minus y is less than delta and xy belongs to A. So thus f is uniformly continuous on A. So this completes our proof for question number 13. Now let us take the question number 14, which is a periodic function. So question number 14 is a periodic. So we are given a periodic function. So we are given a periodic function on R, and the period of R is the length P. So for every point at distance P, their values are equal. So fx is equal to fx plus P for all x belonging to R. We have to show that the continuous periodic function on R is bounded and it is uniformly continuous on R. So we have to show that it is bounded and it is uniformly continuous on R. So proof. So the proof of this theorem depends on the fact that, so for any, so since f is a periodic function, continuous periodic function, with fx equal to fx plus p for all x in R. So for each x belonging to R, there exists y belonging to the interval 0 to p. So for every x, so they, in fact we can write there exists x star. So for every x, because every so because the length of this period is p, because after every distance p the value is repeating itself. So for each x belonging to R, there exists x star belonging to p, such that fx is equal to fx star. So this is due to the period. Fx is equal to fx star. So for each x in R, there exists x star belonging to 0 to p, such that fx is equal to fx star, because our function is a periodic function. So basically what we have done is we have reduced our function to the domain 0 to p. Now f being a continuous function on closed interval 0 to p is bounded on 0 to p. So f is bounded on 0 to p. That is, so basically what it means is that because we have used the result that every continuous function defined on a closed and bounded interval is bounded. So because we are considering the closed and bounded interval 0 to p, so f being continuous, it is bounded on 0 to p. So this implies mod f of x is less than equal to m for all x belonging to 0 to p for some m greater than 0. So there exists some m greater, because f is bounded on 0 to p. So there exists some m greater than 0 such that f of x is less than equal to m for all x belonging to. Now, so we have to show f is bounded on R. We have to show f is bounded on R. So we will use this property that fx is equal to fx star for some 0 to p, because we have to show that f is bounded on R. So for that, let x belonging to R be any point, then there exists x star belonging to 0 to p such that f of x is equal to fx star. So this implies mod fx, which is equal to mod fx star, and fx star belong is less than equal to m, using star since x star belongs to 0 to p. So since x star belongs to 0 to p, so x star satisfies this condition of star, so fx star is less than equal to m. So we have shown that, so since x belonging to R is arbitrary, since x belonging to R is arbitrary, so hence f is bounded on R. So we have shown that f is bounded on R and bound is m. Now what we have to show? Claim 2, f is uniformly continuous on R. So we have to show that f is uniformly continuous on R. Now, so let epsilon greater than 0 be any real number. So we start with any arbitrary epsilon. Now since f is continuous on 0 to p, because we are given that the function f is continuous periodic function. We are given that the function is continuous periodic function. So f is continuous on the interval 0 to p. So by uniform continuity theorem, there exists delta star greater than 0. So by uniform f is continuous on 0 to p. So by uniform continuity theorem, there exists delta star so by uniform continuity theorem, there exists delta greater than 0 such that fx minus fy is less than epsilon whenever, sorry, now since f is continuous on 0 to p, because we are given that the function is continuous periodic function on R. So function is continuous on R. So in particular, function is continuous on 0 to p. So by uniform continuity theorem, f is uniformly continuous on R. So f being uniformly continuous on R, so 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 therefore there exists delta greater than 0 such that fx minus fy is less than epsilon whenever our x minus y is less than delta and xy belongs to the interval 0 to p. So mark it as double star. Now there exists delta greater than 0 such that fx minus fy is less than epsilon whenever your x minus y is less than delta and xy belongs to 0 to p. So f being a periodic function, so now consider any, so we are starting with any xy belonging to R. So we have picked any arbitrary point xy belonging to R with x minus y less than delta. Then as f is periodic, there exists x star y star belonging to 0 to p such that fx is equal to fx star, fy is equal to fy star, and x star minus y star is also less than delta. So because f is periodic, so it takes equal values at a particular period. So we will get 2 points x star and y star in the interval 0 to p, because the period of f is p. So we will get 2 points x star and y star in the interval 0 to p such that fx is equal to fx star, fy is equal to fy star, and x star minus y star is less than delta. So this implies fx minus fy is equal to fx star minus fy star, and because the distance between x star and y star is less than delta, so from this double star, because x star and y star are points of 0 to p and their distance is less than delta, so this will be satisfied. So this will be less than epsilon using double star. So hence, so we started with any 2 points in R, with their distance less than delta, and we are able to show that the distance between their images is less than epsilon. So hence fx minus fy is less than epsilon whenever your xy belongs to R and x minus y is less than delta. So this implies f is uniformly continuous on R. So this completes question number 14. Now let us move to the question number 15. So in question number 15, we are given two Lipschitz function. We have to show that sum of two Lipschitz function is a Lipschitz function. And in the second part, we are given that f and g are bounded on A. We have to show that product is a Lipschitz function on A. And third, we have to give an example of a Lipschitz function on 0 to infinity whose square function is not a Lipschitz function. So let us start with the part A. So to show f plus g is a Lipschitz function on A. So since f and g are Lipschitz function on A, so there exists k1 k2 greater than 0 such that fx minus fy is less than k1 times x minus y and gx minus gy is less than k2 times x minus y for all xy belonging to A. Now let k equal to maximum of k1 k2 then and consider f for all xy belonging to A fx f plus gx minus f plus gy. So we are starting with these two. So this is nothing but fx plus gx minus fy minus gy. Now club and sorry yes now club and use the triangle inequality, we will get fx minus fy plus gx minus gy. So now this is less than k1 times, so this is less than equal to k1 times x minus y plus k2 times x minus y. So replace both. So this is less than k minus plus k times x minus y. So this is equal to 2k times x minus y. So we are able to get this, that this is a Lipschitz function. Or we could have, what we could have done is we could have taken k equal to, instead of taking maximum of this, we could have taken k equal to k1 plus k2. That would have also been, this is also one answer. Or Lipschitz constant can be k1 plus k2. So then this can be written as this is equal to k1 plus k2 times x minus y. So this is much better Lipschitz constant. 2k was also Lipschitz constant where k was maximum of k1 and k2. This is also a Lipschitz constant. So which is equal to k times x minus y. Hence f plus g is a Lipschitz function. Okay, so now we have to take we have to consider part B. So what's there in part B? So we have to show that if f and g are bounded on A, then the product fg is a Lipschitz function. So since f and g are bounded on A, so there exists m1 m2 greater than 0 such that mod fx is less than equal to m1 for all x belonging to A and mod gx is less than equal to m2 for all x belonging to A. Now for any xy belonging to A, consider fgx minus fgy. So this is nothing but your fx gx minus fy gy. So now as we did for product of two continuous functions, so we will take the mixed form. So we will take fx gy, add and subtract fx gy. So this is your fy gy. So we have added and subtracted this term. So this now we will take fx common from here and gy common from here and use the triangle inequality to get this result. So we will get this mod fx using triangle inequality. Now f and g being a Lipschitz function, so this is less than equal to m1 and this is k1 k2 times x minus y plus this is m2, this is k1 times x minus y. So from here what we get is m1 k2 plus m2 k1 times x minus y. So doing this being a constant is a Lipschitz function. So you can take k star x minus y where k star is equal to m1 k2 plus k1 m2. So hence fg is a Lipschitz function. So note that fg product is a Lipschitz function provided the functions are bounded and both are Lipschitz. Now part C, so we have to give an example of a function. So we have to give an example of a Lipschitz function on 0 to infinity such that its square is not a Lipschitz function. So you can take one of the easiest example that, so let fx equal to x on 0 to infinity. Then we know that f is a Lipschitz function. It is easy to see. One can easily Lipschitz function on 0 to infinity. We have already done this. While f square x, which is equal to x square for all x belonging to 0 to infinity, is not Lipschitz. Function on 0 to infinity. It one can easily show this all the things. So fx equal to x is one such example where the function is Lipschitz but square is not a Lipschitz function. So we have done this question number 15. Now let us take the last question of this exercise, which is question number 16. So in question number 16, first we have given a definition. We call a function to be absolutely continuous on an interval if for any epsilon greater than 0 there exists a delta greater than 0, so that for any pairwise disjoint subinterval, so if we take any pairwise disjoint subintervals xk yk of I such that the sum of length of this interval is less than delta, then the corresponding the sum of the corresponding distance of their images is also less than epsilon. So what we are given that we have given that if we take any pairwise disjoint subinterval, so if we take any pairwise, so these subintervals have to be disjoint. These are subintervals of I. They may not be exactly equal to I. So these are sub. So if we take any finite number of subintervals, so disjoint subintervals. So for example, if we have I, this I. If this is our I, okay, so this is suppose AB. This is our I. So I can take this I can take as x1 y1, and I can take another interval x2 y2, and I can take another interval x3 y3, such that the sum of their distances, these three distances, if I add them, it is less than delta. Then their corresponding images, their distance will be less than epsilon. So now we have to show that if f satisfies the Lipschitz condition on I, then f is absolutely continuous on I. So given f is Lipschitz function on I, to show f is absolutely continuous on I. So we start with any pair of disjoint subintervals of I. So since f is Lipschitz function on I, so there exists a Lipschitz constant k greater than 0 such that fx minus fy is less than equal to k times x minus y for all xy belonging to I. So mark it as star. Now because we have to show that f is uniformly continuous on I, so we have to start with any epsilon and we will have to find some delta greater than 0 such that if we take any pairwise subdisjoint intervals xk yk of I with this condition, then we have to show this. So consider, so let epsilon greater than 0 be any real number and let for k equal to 1 to n xk yk be pairwise disjoint subintervals of I. Disjoint subintervals of I. So we have taken pairwise disjoint intervals of I and we have started any epsilon. Now we have to find some delta. So consider, so first we let us consider. So consider summation f of xk minus f of yk. So this we have to show this is less than epsilon. So we started with this, so we start with this. Now we have to bring it in this form so that we can find suitable delta so that this becomes less than epsilon. So this is summation, so this is k times xk minus yk, since f is so from star using star, so this is followed from star using star because we have this, we are given that the function is Lipschitz. Now we can take this k outside and this sum is from k is equal to 1 to n, k equal to 1 to n. So this can be written as, so this is equal to k times summation k equal to 1 to n xk minus yk. So now I have to replace each xk minus yk by less than delta such that this becomes less than epsilon. So I have to take delta equal to, I want this to be less than epsilon. So this should be, so delta, what delta we should choose? We can choose delta equal to epsilon by k. So let delta equal to epsilon by k greater than 0, then by the choice of delta it is evident that summation f of xk minus f of yk is less than epsilon whenever summation xk minus yk is less than delta. So delta equal to epsilon by k, because we wanted a condition on delta, so this should be less than delta, so delta should be epsilon by k so that this all becomes less than epsilon. So hence proved. So this completes our exercise 5.4. So this much is there in this video. Thank you everyone and bye, have a good day.
Thank you for watching this video. To stay updated, please subscribe to our YouTube channel, Cosmos Learning. Happy learning through Cosmos Learning. To watch more, click on any of these cards. Thank you once again.